Hello, beautiful viewers, and welcome once again to another fascinating math video. In this video, we shall be considering a problem taken from mathematical induction. Mathematical induction is a method used to carry out proof on statements regarding positive integers. So if a proposition or a statement is connecting a positive integer, we can prove such a proposition by the use of mathematical induction. All right? We don't just make statements in mathematics. When statements are made, we have to prove them. Hence, there was a video that we solved the problem regarding matrix and we generalized to the results, but we have to prove that generalized result by method of mathematical induction because the problem blends out nicely in the form of regarding the positive integers. So because of that fine blend, we took advantage of that and we were able to use mathematical induction to establish that indeed the result is correct. So over here, we are looking at problems that are strictly on applying mathematical induction. Now, the method is as follows. Firstly, if we are given a problem, so we are given a proposition to prove, to show the truth value of it, the first thing we do, we show that we try to show that the sets for which the statement holds include all positive integers. And how do we show that? We establish firstly that the number 1 satisfies the proposition. Then having established that, we move over to the second stage. The second stage, we suppose that there is a positive integer in that set such that the proposition holds true. Of course, it is, because if we can show that 1 satisfies the proposition, then that positive integer k, that arbitrary positive integer 1, is a qualified candidate. So we suppose that there is an integer k such that the proposition holds true, all right? Then lastly, we from that supposition establish that the proposition is true for when n is equals to k plus 1. If we can do that, then we have shown that the solution set of that proposition is a set of all positive integers rather. So these are the steps we take when carrying out induction, proof by induction. This method is very, very useful. In fact, when you are dealing with analysis, you cannot avoid proof, you must go with proof. And in number theory, this method is exclusively useful. All right, so let's look at the solution of this problem because the battery of my system is getting down now. So the first one, solution. As I said, we create a set for each proposition for which they are true. So we can say let A be the set of all positive integers for which 2n is less than equals to 2 to the power n. Let A be the set of all positive integers for which this proposition holds true. All right. So let us show that 1 is inside the set A. How do we show that? Note that 2 multiplied by 1 is less than or equals to 2 to the power 1. It's true. And because of that reason, since we have already defined A to be the set of all positive integers for which this statement is true. Now, particularly, the statement is true when n is 1, all right? That shows that 1 must be in the set A. So this implies that 1 is an element of the set A, all right? So we've established that already. We are able to make this claim because we define A to be the set of all positive integers for which the statement is true. On substituting 1, we discover that it will be true, and hence 1 must be in the set A. A is called the solution set of the proposition. Now, the next stage is we assume, it's the assumption stage or the hypothesis stage. we assume that there is a positive integer k. So we suppose, let me put it in writing. Suppose that there exists a k in the set A such that, all right, such that 2k rather is less than or equals to 2 to the power k. So that is the supposition. We suppose that there exists an integer k, positive integer k in the set A. Of course, 1 is a very qualified candidate because we have established that 1 is in the set A. So this supposition is not out of place at all. All right. So if you show, are you sure that there exists an integer k for which this statement will be true? Of k can be 1, and that is a very qualified candidate. All right. So we are still in place. This induction axiom is very reasonable. Many occurrence shows that it's very reasonable. Example, the domino theory shows that this axiom for induction is reasonable. All right. You may not find it reasonable because we are not really looking at a detailed explanation, but rather we are solving past question. So I may not have the time to show you an example that will clear your doubts, that will satisfy you. All right. But however, just assume the steps. The first step is to claim that 1 exists in the sets. Having done that, we suppose that there is a positive integer k such that the statement holds true. So now what we shall do, don't forget that 2k less than equals to 2 to the power k is equivalent to writing 2 to the power k bigger than equals to 2k. Hope you know that they're the same thing. All right. So now consider this expression. Consider the expression 2 to the power k plus 1. Just consider that expression. Now from indices, it is a well-known thing that 2 to the power k plus 1 can be written as 2 times 2 to the power k. All right? It's a well-known thing. Now, if I call this star, for example, let me call this star, multiplying both sides by 2 will give us from star. Okay, let me write from star. Multiplying both sides by 2, we have it as 2 times 2 to the power k less than equals to 2 times 2k. All right? Now, from this immediate line, this line, you can see that 2 times 2 to the power k is 2 to the power k plus 1. So I can replace and write 2 to the power k plus 1 in a place of 2 times 2 to the power k. And that is bigger than equals to 2, that is 4k, all right? 4k. And one thing you should observe is that 4k, now listen very well, now 4k is bigger than or equals to 2k plus 2. And this is equals to writing 2 bracket k plus 1. Do you observe that 4k is bigger than it? For any positive integer 1, a k you will take, 4k is bigger than or equals to it. For example, let's put 1 for example. If we put 1 here, we'll have 2 times 2, which is 4. 4 times 1 will give me 4, so all right, that is equality holds. Okay, let's take 2 for example, put 2 here. 2 put 2 here now. 2 plus 1 will give me 3. 3 times 2, 6. Put here will be 8. You see that is inequality holds true, hold in this case. If you put 3, it will become 4 times 2, 8. It will become 12. You see that 4k is always bigger than or equal to 2k plus 1. So in this line, I can write this line as follows. I can write, therefore, 2 to the power k plus 1 is bigger than or equals to 4k, and this 4k is bigger than equal to 2k plus 1. And from the transitivity property of inequality, we can write this as 2 to the power k plus 1 bigger than or equals to 2k plus 1. So what are we saying? We have seen that this is our assumption here. Let me show you now. Look at it. The assumption over here, can you see that? Has established that this holds true. So I can say therefore the hypothesis, which is here's it again, 2 to the power k bigger than or equals to 2k. All right, 2 to the power k bigger than or equals to 2k as implies that 2 to the power k plus 1 is bigger than equals to 2k plus 1. And this is a true implication. All right, it's true. The implication is true. And since it is true, it means that k plus 1 is an element of the set A. All right. So the assumption that the statement is true when n is k has established that k plus 1 will be in the set A. And since that is the case, it follows that the statement is true for all positive integer n. That is, therefore, n is an element of A. In other words, the set A is a set of all positive integers. All right. So by this, we have shown that the statement 2 to the power n bigger than bigger than or equal to 2n is true for all positive integers. We have been able to show that. So this is the idea of a mathematical induction. When carrying out mathematical induction, there are 3 steps. The first step, you show that the statement is true for when n is 1, then you suppose that there is an integer for which the statement is true. And from that supposition, you establish that the statement is true for an integer k plus 1. If you can do that, we conclude by saying that the statement is true for all positive integers. So we're done with this particular one. Let's go to the next because we don't have time any longer. That is 1 plus 2n less than or equals to 3 to the power n. 1 plus 2n less than or equals to 3 to the power n. All right. So we can say let B be the set of all positive integers for which 1 plus 2n less than or equals to 3 to the power n holds. So we show that 1 is in the set B. How do we show that? Now observe that 1 plus 2 brackets 1 is less than or equals to 3 to the power 1. See that in this case equality hold. Hence, we can say that 1 is an element of the set B. All right. So the next thing, we suppose that there exists an integer k which is the set B such that 1 plus 2k is less than or equals to 3 to the power k. All right. And this can be equivalently written as 3 to the power k bigger than or equals to 1 plus 2k. Whichever is the case, they are the same thing. They have the same meaning. They are only equivalent. All right. So we have this. So we can say consider the expression 3 to the power k plus 1. All right. We'll consider this. Now 3 to the power k plus 1 is equals to writing 3 to the power k times 3. Can you see that? Now multiplying this expression over here by 3, I mean this we are seeing here by 3, from that is from the induction hypothesis. From the induction hypothesis, multiplying that by 3, we have that 3 times 3 to the power k is bigger than or equals to 3 times 1 plus 2k. All right. That is to say, 3 to the power k plus 1 is bigger than or equals to 3 plus 6k. All right. Now observe that 3 plus 6k is far bigger than 1 plus 2 brackets k plus 1. Do you observe that? That is bigger. It's not difficult to see. So this is bigger than this. All right. So I can write. Let me remove this from here now. I can say now 3 to the power k plus 1 is bigger than or equals to 3 plus 6k, and this in turn is bigger than or equals to 1 plus 2 bracket k plus 1. All right. By transitivity property of inequality, this can be written as 3 to the power k plus 1 is bigger than equals to 1 plus 2 k plus 1, and which was the assertion originally. In the original problem, we had to prove that 1 plus 2n is less than or equals to 3 to the power of n. This is the same assertion with k plus 1. And this in the place of n, I are putting k plus 1. That means the assumption of the fact that there exists a case so that the statement is true has established that the statement is also true for when the number is k plus 1. And since that is the case, it means that k plus 1 is an element of the set B, all right? It's also there because we've shown that this is true. And if it is true, the number that makes it true, which is k plus 1, must be in the set B. And that shows that this statement is true for all positive integers, all right? And this establishes the claim. These have established the claim. So we prove that this is actually true for all positive integer. Now the last over here we want to look at is still very easy. We have 1 plus 3 plus 5 to 2n minus 1 n squared. I don't like to really waste time here because my battery is gone. Let's just look at this together. We have 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 equals to n squared. We want to show something here, very, very important. Okay, minus 1. Okay, all right. This is number 3. So you can say let this symbol be the set of all positive integers for which 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 is equals to n squared. All right. So let's show that 1 is in that set. How do we show that? To show that 1 is there, we take the case where n is 1. And if n is 1, we shall be having the first term we shall be having will be 2 brackets 1 minus 1. And that is equals to 1 squared. Is it not true? It is true. Since that is true, it implies that 1 is an element of this set. All right. So the next thing, we suppose that there exists a k in the set, this entity, such that the statement is true, such that 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 is equals to k squared. All right, we suppose that this is the case. Now, from this supposition, we establish that the statement is true for k plus 1. All right, and we can say to establish that, we consider the expression, 1 plus 3 plus 5 plus dot 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 plus 2k minus 1. Next will be plus 2 brackets k plus 1 minus 1. Let's consider this expression. All right. Now, don't forget that 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 plus 2 brackets k plus 1 minus 1 can be equally written. I'm trying to be fast in order to, my battery is almost gone. 1 plus 3 plus 5 plus dot 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 plus 2k minus 1, then plus brackets 2k plus 1 minus 1. All right, can you see that? So we have this as the result. Now, this from the induction hypothesis, this expression here is equals to k squared. Can you see that here? Look at it here. K squared. So I can come here and write this is equals to k squared plus 2 bracket k plus 1 minus 1. So an expansion, we have k squared plus 2k plus 2 minus 1, all right? And further expansion yields k squared plus 2, sorry, further simplification. Further simplification. Let me remove this from here. This is previous work. Oh, all right. So now this is a quadratic. Factoring this will give us k plus 1 to the power 2. All right. So we've established, therefore, we've seen that 1 plus 3 plus 5 plus dot 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 2k minus 1 plus 2 brackets k plus 1 minus 1 as yield k plus 1 to the power 2, and which is the proposition, the original proposition, but this time around replaced with k plus 1. Compare this we have now with the case when it was n. You see that they are the same thing. All right, look at it here. Compare this with this. You see that it's the same proposition, just that is asserting this based on when the number is k plus 1. And since this follows from our hypothesis, that is our supposition, it follows that the implication is true. And since the implication is true, we have that k plus 1 is also an element of a set entity. And if that is the case, this assertion is true for all positive integer n. And this concludes the proof. All right. So this method of proof is very, very important and is only applicable to positive integer. So if you have a proposition involving positive integer, be sure that mathematical induction is a very plausible method to use to carry out its proof. It's very, very interesting, very, very useful. All right. So have a good day. Make sure you go through the video once, twice, thrice for proper graphs. If there's any point you did not get, you can get back to me. Comment on the comment section so that we can bring clarity. Don't forget, I render an exclusive online math tutoring service. If you are interested in such a service, be very free to get across to me so I will make arrangements regarding how the class will be like. In such a class, we give detailed explanation. If you are allowed to talk, you can ask me a question of your sort, of any sort. Any points you're not clear, you ask me, I'm going to provide a solution to you for you. So thank you very much for paying attention. Till next time.